This lecture talks about two sample tests other than the t-test. The first test is a test of medians. It's a non-parametric test that can be used for ordinal type data as well as measurement data. It's the Wilcoxon Rank-Sum Test. The idea here is to compare the medians of two independent samples using ranks. Okay, rank is just the position of an item in an ordered list. So here's two samples, blue and white. And some possible orderings. So we can have the two blues be the first and second, or it can be the first and third, or the first and fourth, or the first and fifth, and so on until we finally get the two blues to be the fourth and fifth. What we do is we rank them 1 through 5, independent of group, and then we add up the ranks for the blue group. And so we get a sum of the ranks that ranges from 3 to 9. Obviously, when the sum is 3, blue is ahead of white. When the sum is 9, white is ahead of blue. Let's see how this works to do a test. The test statistic, W, is just the sum of the ranks for one group. For small samples, we can just look up the sum in a tabulated list of p-values. This is relatively easy to generate with computer software, but it's a bit of a chore. For larger samples, sample sizes greater than 10, there's a Gaussian approximation, and the approximation is really nice because it's just based on the sample sizes. So we have a formula for the expected value, we have a formula for its variance, and then we just calculate a z-score. It works because for large samples, if we look at the frequencies of the possible sums, we see that this converges to a Gaussian. So let's look at an example. We have this problem where we wanted to know if talking elevated blood pressure when you're having your vitals taken in the doctor's office. We're going to test this at the 5% level, and we're going to do a two-sided test. We'll do a two-sided test here today. And so we'll use 2.5% on either tail, and that'll give us a critical value of 1.96. So here's our measurements. Here's our measurements for the talking and counting groups. And we've ranked them. So the smallest value, number 1, is in the counting group, and so is 2, 3, and 4. And then 5 and 6, one's in the counting group, one's in the talking group. And what we do is we average those two ranks, 5 and 6, average to 5.5. And we continue through all the data. All right. What we see then is that one group has a sum of 49 and the other has an 87. We can actually use either one when we do our test, especially when we're doing a two-sided test. So let's go ahead and calculate our mean and standard deviation. Sample sizes are 8, so I'm cheating here a little bit because I said bigger than 10, but we're just doing this for purposes of illustration. And so 8 times 8 plus 8 plus 1 divided by 2 gives us 68 for the mean. 8 times 8 times 17 divided by 12. And take the square root. We get a standard deviation of 9.52. 12. That's a crazy number that shows up a lot in counting type distributions. And then we just calculate the z-score. So we'll take the 87, subtract off the mean, divide through by the standard deviation, and we'll get a z-score of 1.996, which is greater than the critical value. And so we'll reject the null hypothesis. And talking gives different blood pressure readings. I say different because it was a two-sided test. So that actually compares medians. Now, the two-sample t-test compares means. Something else we can compare that's a continuous value is proportions. And if we're comparing proportions from independent samples, then we want to know, okay, are the proportions greater than or less than or not equal? With a null hypothesis that always includes equality of the proportions. These are usually done for large samples. So it's a z-test. Now, under the null hypothesis, the two proportions are equal. So we need to compute the standard error under the null hypothesis. We'll do that using a pooled proportion. Ooh, so this is like the two-sample t with equal variances. All right. So we'll calculate the proportion for each group, and then the pooled proportion basically says combine all the successes and divide that by the combined sample sizes to give a pooled proportion. And so this number gets used down here, and these two numbers get used in the top. All right. So let's look at an example here. We're recording this in the midst of the COVID-19 quarantine, so we've got some interesting numbers to play with. On the 2nd of April, I looked to compare the COVID-19 death rates for Houston and San Antonio. We want to test this at the 5% level. Again, I'll do a two-sided test, so critical value will be 1.96. So as of April 2nd, Harris County had 608 cases with 6 deaths for a proportion of 0.0088, so slightly under 1%, while Bexar County had 207 cases with 9 deaths, so a rate of a little over 4%. They certainly look different. So let's go ahead and calculate the pooled proportion. So we'll add the 6 and the 9 in the numerator. We'll add the 208 and the 608 and 207 in the denominator. And we'll get a pooled proportion of 0.0169. So yeah, it's in between the other two proportions. So that's a good indication. Now we'll do the test. So we'll take the individual proportions in the numerator. We'll take the pooled proportion in the denominator along with the two sample sizes. This is just a bit of a chore when we're using a calculator, but not anything terribly difficult. When we run through the calculator, we get minus 3.391, which is a lot less than the negative critical value. So we'll reject the null hypothesis and say the rates differ. Ooh, bad news for me. I'm here in San Antonio. Now, another thing we can test from two samples are variances. This can be used to justify the pooled variance version of the two-sample t. What a waste of time. Now, comparing variances is really quite easy. We really want to know this sometimes. Again, I'm going to say wait for ANOVA. So when you start studying ANOVA, you'll see that we do this test a lot. Since variance is a measure of scale rather than differences, we use ratios okay, rather than differences. We're going to use what's called the folded f-test. We're going to do a little trick to make this into a one-sided test, so it's really, really easy. The test statistic calls what's called the f-distribution, which is a ratio of chi-squares, okay, which are variances. Okay, it's a skewed distribution with shapes like this, and the expected value, okay, the mean is approximately 1 under the null. So what's our test statistic? What's our test statistic? We take the ratio of the two sample variances, put the largest one on top. Large one on top. And the result is it follows an F distribution with degrees of freedom from each one. So n1 minus 1 and n2 minus 1. It's that simple. It's that simple. Let's look at an example. I've got 10 water wells that were tested for trichloroethylene contamination before and after remediation. Now, if I were comparing means, this would be a paired t-test, right? But we're not comparing means. We want to see how variation has changed. So we're going to look at the two variations, 183 before, 12.6 afterwards, same sample size, 10. So then the critical value, we'll just look this up in the F table or use R. And we find that critical value to be 3.179. And for those of you that are looking at this, we can use the QF function in R, give it the percentage point and the 2 degrees of freedom, and we'll get the answer. Okay, so that'll give us that number. Then the test statistics, just the ratio of these two, which is 14.52, which is lots greater than the critical value. So reject the null hypothesis. Variances differ. Obviously.